Look up, really look up at the night sky tonight, and you'll see more than just pinpricks of light. Every star out there is a story, a fiery epic of birth, life, and sometimes violent death, written across the canvas of space. But here's the thing, those stories aren't just happening out there, they're the reason you exist. The atoms in your body, the oxygen in your lungs, even the screen you're staring at right now, all of it was forged in the hearts of stars and scattered across the cosmos by nebulas, those glittering clouds of gas and dust that serve as both cradles and graveyards for the universe's most dazzling objects. Now, what if I told you that everything we think we know about the life cycle of stars might just be the tip of the iceberg, that there are theories out there, 25 of them, in fact, that could rewrite the rules of how stars live, die, and rebirth themselves in ways that defy imagination. Picture this, a star so massive it doesn't just collapse into a black hole, it unravels space-time itself, or a nebula that doesn't just create new stars, but recycles the remnants of dead ones into something entirely alien. These aren't scenes from a sci-fi novel. They're real, cutting-edge ideas being explored by astronomers right now, and they're about to change how you see the universe. So why does any of this matter? Because the cosmos isn't some distant spectacle. It's alive, dynamic, and intimately connected to us. Every time a star explodes, it seeds the galaxy with the building blocks of planets and life. Every nebula is a chapter in a story that began billions of years ago and continues to unfold tonight, right above your head. And that's where our journey begins. Over the next 25 revelations, we'll travel from the swirling stellar nurseries where stars are born to the violent, beautiful deaths that light up the cosmos. You'll discover why some stars fade silently into the dark while others go out with a bang so powerful it can outshine entire galaxies. You'll see how nebulas aren't just pretty cosmic decorations, they're the engines of creation itself. And by the time we're done, that night sky, it won't just be something you glance at, it'll be a story you understand, a story you're part of. So let's begin. The Orion Nebula, that glowing smudge in the night sky you've probably glimpsed through binoculars, isn't just a pretty cosmic cloud. It's a factory, a relentless, churning factory where stars are born. Inside its swirling depths, hydrogen and dust collide, pulled together by gravity's invisible hand until they form knots so dense, so hot, that nuclear fusion ignites like a match struck in the dark. But here's the twist, this isn't some orderly assembly line. It's chaos with purpose. Take those delicate tendrils of gas you see in Hubble's famous images. They might look serene, but they're actually battle zones where magnetic fields and turbulence wage a silent war. Picture a whirlpool in space, one where gravity tries to collapse the gas into stars, while magnetic forces push back, twisting and braiding the material like cosmic taffy. This tug of war determines whether a newborn star will be a modest red dwarf or a colossal blue giant. And sometimes, when the conditions are just right, the nebula doesn't create one star, it spawns a litter. The trapezium cluster in Orion, for instance, is a stellar kindergarten with over 1,000 infant stars, some still wrapped in their dusty cribs of gas. But the real magic happens in the shadows. Deep within these nebulas, hidden from visible light, radio telescopes have spotted something extraordinary. Vast filamentary structures, like cosmic spiderwebs channeling gas into star-forming hubs. It's as if the nebula itself is directing traffic, herding raw materials into the perfect spots for stellar birth. And when those stars finally flare to life, their fierce winds carve cavities in the nebula, sculpting it into those iconic shapes we recognize. So next time you see a nebula, remember, you're not just looking at a cloud, you're witnessing the universe's most spectacular cradle, where chaos and creation collide to light up the cosmos. That glowing protostar hidden deep within its cocoon of gas isn't yet a true star, not quite. It's more like a cosmic toddler stumbling through its first steps toward brilliance. Imagine a sphere of hydrogen collapsing under its own weight, growing hotter and denser until its core becomes a roiling cauldron of pressure, but without the nuclear fires that define a mature star. This is a place of raw potential, where gravity's relentless pull battles the outward push of heat and magnetic fields in a showdown that will determine whether this object becomes a modest dwarf or a blazing giant. Now zoom in closer. That swirling disk of dust and gas surrounding the protostar isn't just debris, it's a planetary construction site. Particles collide, stick together, and slowly build the seeds of future worlds. But here's where things get wild. Twin jets of superheated gas often erupt from the protostar's poles, shooting light years into space like cosmic blowtorches. These aren't random outbursts. They're the star's way of shedding excess energy as it fights to find balance. Picture a spinning figure skater pulling their arms in, except this skater is hurling plasma at nearly the speed of light, carving intricate loops and knots into the surrounding nebula. Then comes the T-Tauri phase, stellar adolescence at its most volatile. The star's magnetic field becomes tangled and fierce, flinging massive flares that can outshine the star itself for days. Its rotation slows as it sheds material, and the disk around it starts to thin, either blown away by stellar winds or locked into newborn planets. This is the tipping point. Either gravity wins, crushing the core enough to ignite hydrogen fusion and birth a stable star, or the protostar falters, becoming a brown dwarf, a failed star glowing dimly with only the embers of its potential. What's astonishing is how much this chaotic childhood shapes the star's future. A protostar that consumes its disk too quickly might grow into a massive, short-lived star destined for a supernova. One that forms in isolation could become a steady, long-lived red dwarf, and sometimes the leftover material from this turbulent phase becomes the very planets that might one day harbor life. So when you gaze at a mature star, remember, its brilliance was hard-won, forged in the fires of a youth more dramatic than any coming-of-age story. Main sequence stars are the universe's marathon runners, steady, reliable, and in it for the long haul. Picture our sun, that familiar yellow disk in the sky, quietly converting hydrogen into helium for billions of years without so much as a dramatic flicker. This is the stellar equivalent of adulthood, where a star settles into its prime, balancing gravity's inward pull with the outward pressure of nuclear fusion. But not all stars age the same way. Their lifespans aren't just about time, they're about temperament. Take a red dwarf, for example. These petite, cool stars are the ultimate misers, hoarding their hydrogen fuel with such thriftiness that they can shine for trillions of years. Their cores churn like slow cookers, recycling material so efficiently that some of these stars, born when the universe was still in its infancy, might outlive every other object in the cosmos. They're the quiet survivors, glowing faintly but persistently long after their flashier cousins have flamed out. Now contrast that with a blue supergiant, a celestial titan burning so hot it could vaporize a planet just by proximity. These stars live fast and die young, squandering their fuel in a cosmic sprint that lasts just a few million years. The difference, mass. A star's weight determines its appetite. The more massive a star, the fiercer the fusion in its core, like a furnace cranked to maximum. That intensity comes at a cost. It devours hydrogen at a staggering rate, shortening its lifespan exponentially. Our Sun, it's middle of the road with a respectable 10 billion-year main sequence tenure, but a star 50 times heavier. It's already on borrowed time. Here's the fascinating part. This balancing act isn't just about fuel. A star's internal structure changes with mass. Smaller stars are fully convective, stirring their hydrogen like a pot of soup, ensuring nothing goes to waste. Bigger stars, though, fuse hydrogen only in their cores, leaving outer layers untouched until later stages. It's the difference between a frugal chef using every scrap and a banquet hall tossing out untouched platters. And then there's metallicity, the star's chemical makeup. More heavy elements mean more opacity, which changes how heat moves through the star, subtly altering its lifespan. It's like two cars with identical tanks but different engines. One might sip fuel while the other guzzles it. So when you look up at the main sequence stars tonight, remember, their brilliance isn't just about light. It's a countdown clock ticking at speeds written in their very DNA. Some are barely past dawn, while others are already racing toward sunset. When a star runs out of hydrogen fuel in its core, it doesn't just fade away, it throws a cosmic tantrum. The once stable balance between gravity and fusion collapses, and the star responds by swelling into a red giant or supergiant, inflating to hundreds or even thousands of times its original size. Imagine our Sun, billions of years from now, growing so large that it swallows Mercury, Venus, and possibly Earth in a slow-motion inferno. But this expansion isn't just about size, it's a desperate survival tactic. Deep inside the star's core, helium, the ash of spent hydrogen starts fusing into heavier elements like carbon and oxygen. This new energy source burns hotter and more violently, pushing the star's outer layers outward with irresistible force. The outer shell of hydrogen, no longer anchored by a stable core, puffs up like a balloon, cooling as it expands and giving the star its distinctive red hue. For smaller stars like our Sun, this phase lasts a few 100 million years before they shed their outer layers entirely. But for massive supergiants like Betelgeuse, the stakes are higher. These behemoths don't just expand, they become unstable, pulsating unpredictably as they teeter on the edge of catastrophe. What's fascinating is how these aging giants recycle the universe. As they expand, their stellar winds grow stronger, blowing vast amounts of gas and dust into space. This material, enriched with heavier elements forged in the star's core, becomes the raw material for future stars and planets. The carbon in your DNA, the oxygen you breathe, much of it was cooked inside a red giant long before Earth existed. And then there's the ticking time bomb of Betelgeuse. This red supergiant, a shoulder in Orion's constellation, has dimmed and brightened erratically in recent years, sparking debates among astronomers. Is it about to go supernova? If it does, the explosion could outshine the moon in our night sky, visible even by day. But timing is everything. It could happen tomorrow or 100,000 years from now. That's the paradox of these giants. Their final acts are both inevitable and unpredictable. Inside these swollen stars, the core is a battleground. Gravity crushes atoms together, forming ever heavier elements until iron starts to pile up, a death knell for the star. Iron doesn't release energy when fused. It absorbs it, starving the core of its last defenses against collapse. When that tipping point comes, the star's fate is sealed. Whether it quietly sheds its skin to form a planetary nebula or detonates in a supernova, one thing's certain: the end of a red giant isn't an ending at all. It's a transformation, one that lights up the cosmos with the ingredients for new beginnings. Planetary nebulas are the universe's way of turning a star's death into a masterpiece. When a sun-like star exhausts its nuclear fuel, It doesn't just vanish, it stages one final, breathtaking performance. The star's outer layers, once held in place by the delicate balance of gravity and fusion, drift away like cosmic smoke, illuminated by the intense ultraviolet light of the exposed core. This is no chaotic explosion. It's a slow, elegant unraveling, a stellar swan song that can last tens of thousands of years. Take the ring Nebula, for instance. From a distance, it looks like a perfect celestial halo, a glowing loop suspended in space. But zoom in, and you'll see intricate structures, delicate filaments, knots of gas, even symmetrical bubbles, all sculpted by forces we're only beginning to understand. The name Planetary Nebula is a historical accident coined by early astronomers who thought these glowing orbs resembled distant gas giants. The truth is far more poetic. These are the fingerprints of dying stars, their expelled atmospheres frozen in time. So how does a sphere of hot gas transform into such intricate shapes? One theory points to magnetic fields, invisible threads woven through the star's outer layers. As the star sheds material, these fields act like cosmic cookie cutters, channeling the gas into lobes, rings, and even hourglass figures. Another possibility involves binary companions. If the dying star has a partner, their gravitational dance could warp the outflow, twisting it into spirals or jets. Some planetary nebulas, like the Butterfly Nebula, display breathtaking symmetry, wings of gas stretching light years across, as if the star took flight in its final moments. What's truly remarkable is the chemistry at work here. The exposed core, now a white dwarf, bombards the ejected gas with radiation, causing it to fluoresce in vivid hues. Oxygen glows green, nitrogen burns red, and hydrogen paints the sky blue. These nebulas aren't just pretty, they're cosmic alchemy labs, enriching the galaxy with elements that will one day form new stars, planets, and perhaps even life. And then there's the mystery of variability. Some planetary nebulas, like the cat's eye, contain concentric shells, evidence of multiple outbursts spaced thousands of years apart. It's as if the star hesitated, exhaling in fits and starts before finally falling silent. Others, like the Helix Nebula, stretch so wide they're nearly invisible from Earth, their faint glow only revealed through long exposure telescopes. But here's the humbling part. These nebulas are fleeting. Over millennia, the gas disperses, fading into the interstellar medium. The white dwarf at the center cools into oblivion, a dim ember in the cosmic dark. Yet in that brief window, a cosmic blink, the star's farewell becomes a beacon, a reminder that even in death there's beauty. So the next time you see an image of a planetary nebula, remember, you're not just looking at a dead star. You're witnessing a cosmic legacy written in light and gas, a final act of creation before the curtain falls. A white dwarf is the universe's way of turning a star's death into a whisper, a slow, lingering fade into the cosmic dark. After a sun-like star sheds its outer layers in a planetary nebula, what remains is a core so dense that a single teaspoon of its material would weigh as much as an elephant. Yet despite this incredible density, a white dwarf is no larger than Earth, packing the mass of a star into a sphere the size of a planet. It's the ultimate cosmic paradox, a relic that burns with residual heat but no longer generates new energy, destined to cool over trillions of years like a dying ember. But don't mistake this quiet for inactivity. Some white dwarfs have a second act, one fueled by cosmic theft. If a white dwarf orbits close enough to a companion star, its gravity can pull material away, siphoning hydrogen like a vampire. This stolen gas accumulates on the dwarf's surface, compressing under its immense gravity until it reaches a critical temperature, and then, suddenly, it detonates. The result, a nova, a thermonuclear blast bright enough to outshine an entire galaxy for weeks. Unlike a supernova, the white dwarf survives this explosion, only to repeat the cycle again and again, flaring back to life whenever it steals enough fuel. Yet even more bizarre is what happens inside these stellar corpses. Over time, the intense pressure forces carbon and oxygen in the white dwarf's core to crystallize, forming a lattice structure akin to diamond. Imagine a star's core hardening into a planet-sized gem, glittering in the darkness, a diamond older than the galaxy itself. Some astronomers estimate that up to 90% of white dwarfs may undergo this transformation, their interiors turning into crystalline spheres colder than ice. But the real mystery lies in their ultimate fate. Given enough time far longer than the current age of the universe, a white dwarf would radiate away all its heat, becoming a black dwarf, a cold, dark mass drifting silently through space. The catch: none should exist yet. The universe simply hasn't been around long enough for even the first white dwarfs to cool completely. So for now, these stellar ghosts continue to glow faintly, their light a reminder of the fires that once burned within them. What's astonishing is how much these quiet objects reveal about the cosmos. By studying white dwarfs, astronomers can measure the age of the galaxy, trace the history of star formation, and even uncover the composition of long-dead stars. They're cosmic time capsules, preserving elements like carbon, oxygen, and neon in their atmospheres, elements that were forged in their cores and will one day be recycled into new stars and planets. So while a white dwarf may seem like the end of a story, it's really just a pause, a bridge between the death of one star and the birth of countless others. Supernovas are the universe's grand finale, a star's final, defiant act of self-destruction so powerful it can outshine an entire galaxy. Imagine a single cosmic event releasing more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime. This isn't just a star dying, it's a star rewriting the rules of existence. When a massive star exhausts its nuclear fuel, gravity wins the battle it's been waging for millions of years, and the core collapses in a fraction of a second. The outer layers, no longer supported, crash inward at unimaginable speeds, then rebound in a shockwave so violent it rips the star apart. The result: a fireball brighter than a billion suns, hurling stellar material into space at nearly 1/10 the speed of light. But here's the twist: this isn't just destruction. It's creation. The intense heat and pressure in those fleeting moments forge elements heavier than iron, gold, platinum, uranium, elements that can't form in the gentle fusion of living stars. Every piece of jewelry you've ever worn, every ounce of precious metal in your electronics, even the radioactive fuel in nuclear reactors, all of it was born in the heart of a supernova. These explosions are the universe's alchemists, turning the simplest atoms into the building blocks of planets and life itself, and their influence doesn't stop there. The shockwaves from a supernova can slam into nearby molecular clouds, compressing them until they collapse into new stars. It's a cosmic chain reaction. One star's death becomes the spark for another's birth. The Crab Nebula, the remnants of a supernova observed on Earth in 1054, is a perfect example. Inside its swirling filaments, astronomers have found a pulsar, a rapidly spinning neutron star, powering the nebula's glow like a cosmic lighthouse. The surrounding gas, enriched by the explosion, is a nursery for future stellar generations. Yet the most astonishing part: supernovas might hold clues to life's origins. The same heavy elements they scatter are essential for DNA, for oceans, for rocky planets like Earth. Without these titanic explosions, life as we know it wouldn't exist. Some theories even suggest that nearby supernovas could have influenced Earth's evolution, their radiation potentially triggering mutations that accelerated biological diversity. So when you look up at the night sky, remember, the same violence that obliterates stars also made your very existence possible. It's a reminder that in the cosmos, death and creation are two sides of the same coin, and supernovas are the ultimate proof. When a supernova's fury subsides, what remains isn't just emptiness, it's a cosmic enigma so extreme it defies everyday logic. Meet the neutron star, a stellar corpse where matter has been crushed into oblivion. Picture this, an object no wider than Manhattan, yet containing more mass than our Sun, squeezed so tightly that protons and electrons fuse into neutrons, creating a substance denser than anything else in the universe. A single sugar cube-sized chunk of this material would weigh as much as a mountain, billions of tons compressed into a space smaller than a raindrop. But neutron stars aren't just dense, they're dynamos of wild physics. Some of them spin at dizzying speeds, rotating hundreds of times per second despite their immense mass. These rapid spinners, known as pulsars, emit beams of radiation from their magnetic poles. As the star whirls, these beams sweep across space like lighthouse beams, appearing to pulse when detected from Earth. The Crab pulsar, born from the same supernova observed in 1054, still spins 30 times every second, its rhythmic flashes so precise they rival atomic clocks. Then there are the magnetized neutron stars with magnetic fields so strong they could erase credit cards from halfway across the solar system. These fields, a quadrillion times more powerful than Earth's, twist the star's crust until it fractures in starquakes, releasing bursts of gamma rays brighter than 100,000 suns. In 2004, a magnetar 50,000 light-years away unleashed a flare so intense it briefly ionized Earth's upper atmosphere, even from that staggering distance. But the real mystery lies beneath their surfaces. The crushing gravity of a neutron star warps the very fabric of space-time, creating conditions so extreme that physicists speculate they might harbor exotic states of matter, like nuclear pasta, where protons and neutrons arrange themselves into shapes resembling spaghetti or lasagna under unimaginable pressure. Some theories even suggest that the cores of the most massive neutron stars might collapse further into quark-gluon plasma, a primordial soup of particles not seen since the universe's first microseconds. And here's where things get even stranger. Neutron stars could be the key to unlocking quantum gravity, the long-sought theory that would unite Einstein's relativity with the quantum world. Their intense gravity and quantum-scale density make them natural laboratories for testing physics beyond our current understanding. When two neutron stars collide, an event detected in 2017, the resulting gravitational waves and kilonova explosion scattered heavy elements like gold and platinum across the cosmos, proving these collisions are cosmic forges for the universe's rarest materials. Yet for all their ferocity, neutron stars are fleeting. Over billions of years, they'll slowly cool, their relentless spin fading as they radiate away energy. Some may eventually become black holes, their gravity finally overwhelming even neutron degeneracy pressure. But for now, they remain some of the most extreme and enigmatic objects in existence, reminders that the universe's most astonishing wonders often lurk in the ashes of catastrophe. Black holes aren't just the end of a star's story, they're the ultimate cosmic paradox. When a star many times heavier than our Sun collapses under its own gravity, it doesn't stop at becoming a neutron star. It keeps crushing inward until space-time itself warps into a singularity, a point of infinite density where the laws of physics as we know them break down completely. Surrounding this unfathomable pit is the event horizon, a boundary so absolute that once anything crosses it, there's no going back. Not light, not matter, not even time. It's the universe's most ruthless one-way door. But here's where things get strange. For decades, scientists thought black holes were simple, defined only by their mass, spin, and charge. The rest, as physicist John Wheeler famously put it, was bald. Black holes have no hair, yet recent theories suggest they might be far more complex. Quantum mechanics hints that information, the fundamental stuff of particles and their states, can't just vanish. So if black holes swallow everything, where does that information go? Some researchers argue that black holes might have subtle features, or hair, after all, tiny imprints of what falls into them, etched into their event horizons like cosmic fingerprints. Then there's the firewall paradox. Imagine falling toward a black hole. According to Einstein's relativity, you'd pass the event horizon unharmed, stretched by tidal forces in a process whimsically called spaghettification. But quantum physics suggests something far more violent, a wall of ultra-high energy particles at the horizon, incinerating anything that approaches. These two theories can't both be right, and resolving this contradiction might require rewriting our understanding of reality itself and what lies beyond the event horizon. Some hypotheses border on science fiction. Could black holes be tunnels to other universes, wormholes disguised as cosmic traps? The math allows for it, but the journey would be fatal. Others speculate that black holes might birth new universes inside them with their own laws of physics. It's a dizzying thought. Our entire cosmos could be the offspring of a black hole in some other, older universe. Yet for all their mystery, black holes aren't just destructive. They're cosmic architects. Supermassive black holes lurking at the centers of galaxies shape the stars around them, their gravity orchestrating stellar orbits like invisible conductors. When two black holes collide, they send ripples through space-time itself, gravitational waves we can now detect here on Earth. These collisions are so violent they briefly outshine all the stars in the observable universe combined. Perhaps the most mind-bending idea, black holes might not last forever. Quantum theory predicts they slowly evaporate, leaking energy in the form of Hawking radiation, a process so slow that a typical black hole would take longer than the current age of the universe to vanish. But in the far, far future, the last light in the cosmos might come from dying black holes, whispering their final secrets into the void. So while black holes may be the darkest objects in existence, they're also among the most illuminating. They force us to confront the limits of our knowledge, daring us to imagine what lies beyond the edge of understanding. Every question they answer seems to spawn 10 more, and that's what makes them the ultimate frontier of astrophysics. Dark matter doesn't just lurk in the shadows of the cosmos. It might be pulling the strings behind the scenes, shaping the very stars we admire. Imagine an invisible hand guiding the birth and death of celestial objects, its presence felt only through gravity's subtle tug. While we can't see dark matter directly, its gravitational influence is undeniable, weaving through galaxies like an unseen scaffold. But here's the provocative question. Could this mysterious substance be doing more than just holding galaxies together? Could it be altering the life cycles of stars themselves? One daring theory suggests dark matter particles might accumulate in the cores of stars, like invisible embers smoldering beneath the surface. In massive stars, these particles could collide and annihilate, releasing energy that counteracts gravity's crush. The result, a star that burns longer, cooler, or even avoids collapse into a black hole entirely. It's as if dark matter is a cosmic thermostat, subtly dialing up or down the fate of stellar giants. For smaller stars like red dwarfs, dark matter could act as an extra fuel source, slowing their aging process to a crawl. Picture a star that outlives its expected lifespan by billions of years, not because of its own nuclear fires, but because of the invisible particles simmering within it. Then there's the grander scale dark matter halos, those vast, invisible clouds enveloping galaxies. These halos aren't just passive bystanders, they could be the architects of star formation. As ordinary gas and dust swirl through a galaxy, the gravity of dark matter might corral it into dense pockets, triggering the birth of new stars. Some astronomers even speculate that without dark matter's guiding hand, galaxies would lack the structure needed to form stars efficiently. The iconic spiral arms of galaxies, the glittering trails of newborn stars, they might all trace back to the invisible blueprint of dark matter, but the most mind-bending idea. Dark matter could explain some of the universe's greatest mysteries, like why certain galaxies produce stars far earlier than our models predict. If dark matter interacts with itself in ways we don't yet understand, it might create dark nebulas, invisible clouds that collapse under their own gravity, seeding the cosmos with stars before conventional physics says they should exist. Observations of ancient galaxies brimming with stars when the universe was barely a toddler hint that something, perhaps dark matter, jump-started the process. Of course, these theories are still on the fringe, challenging decades of astrophysical wisdom. Detecting dark matter's influence on stars is like trying to hear a whisper in a hurricane. Yet the tantalizing clues are there: odd stellar motions, unexplained energy signatures, galaxies that defy gravitational expectations. Each anomaly is a breadcrumb leading us closer to understanding dark matter's true role. So the next time you gaze at the night sky, remember, the stars you see might be more than just nuclear furnaces. They could be cosmic collaborations, their lives shaped by forces we're only beginning to imagine. Dark matter isn't just a missing piece of the universe, it might be the hidden choreographer of the stellar dance, silently orchestrating the rise and fall of galaxies. And if we're right about its influence, uncovering its secrets could rewrite the story of how everything from the smallest star to the grandest nebula came to be. Binary star systems are the universe's ultimate cosmic tango, a gravitational waltz where two stars orbit each other, sometimes so closely that their fates become inextricably linked. Take Sirius, the brightest star in our night sky. What looks like a single pinpoint of light is actually a duo, Sirius A, a blazing main sequence star, and Sirius B, a faint but incredibly dense white dwarf. These two couldn't be more different, yet they're locked in a slow, relentless dance that's lasted hundreds of millions of years. But this partnership isn't just celestial eye candy, it's a laboratory for some of the most violent and creative processes in the cosmos. When binary stars are born close together, their relationship can turn volatile. Imagine one star expanding into a red giant, its outer layers spilling over onto its companion like an overflowing cup. This stolen material doesn't just vanish, it piles up on the smaller star, triggering eruptions or even supernovas if enough mass accumulates. In some cases, the donor star gets stripped down to its bare core, transforming into a helium star or white dwarf long before it would have on its own. It's cosmic vampirism on a grand scale, where one star's growth comes at the other's expense. Then there's the spectacle of merging binaries. Picture two stars spiraling inward, their orbits decaying over millennia until gravity finally forces them to collide. The result, a cataclysmic explosion or the birth of a brand new, more massive star. Some of the universe's brightest blue straggler stars that defy age by appearing younger and hotter than their surroundings are thought to be the products of such stellar mergers. Others might collapse directly into black holes, their combined mass too great to resist gravity's crush. But the real drama unfolds in systems where one star is already dead. A neutron star or black hole orbiting a living star can siphon material so efficiently that it forms an accretion disk, a swirling vortex of superheated gas that glows with X-rays. These X-ray binaries are among the most energetic objects in the galaxy, their emissions detectable across interstellar distances. And if the dead star is a pulsar, its intense magnetic field can whip the stolen material into jets that shoot out at nearly the speed of light, carving intricate patterns into the surrounding nebula. Yet binary systems aren't just agents of chaos, they are also cosmic recyclers. The material exchanged between stars enriches the interstellar medium with heavy elements, seeding future generations of stars and planets. Some theorists even suggest that tight binary interactions could explain certain types of supernovas that don't fit the standard models, like those that leave no remnant behind. What's fascinating is how these duos challenge our assumptions about stellar life cycles. A star in a binary system doesn't age in isolation. Its fate is shaped by its partner's presence, whether through gentle nudges or violent theft. From the quiet ballet of wide binaries to the explosive pass-to-due of merging stars, these systems remind us that in the cosmos, no star is truly alone. And when their dance reaches its climax, the aftermath can light up the galaxy. Deep within the crowded hearts of globular clusters, ancient, dense swarms of stars orbiting galaxies like cosmic bees around a hive, stellar survival takes a brutal turn. Here, stars don't just shine peacefully, they brawl. With hundreds of thousands of stars crammed into a space just a few light years across, close encounters aren't just likely, they're inevitable. And when two stars cross paths, gravity doesn't play favorites. It orchestrates a celestial showdown where the winner takes all: mass, energy, even destiny itself. Enter the blue stragglers, stars that defy time. These celestial anomalies glow hotter and bluer than their cluster neighbors, appearing decades or even billions of years younger than they should be. How they've cheated death by stealing life from others. Picture two aging stars circling each other in a gravitational embrace. As one expands into a red giant, its outer layers drift dangerously close to its companion. The smaller star, like a cosmic parasite, siphons off this material, bulking up with fresh hydrogen fuel. The result, a reinvigorated star, burning brighter and hotter as if it's turned back the clock. But theft isn't the only path to rejuvenation. In the tight quarters of a globular cluster, full-on collisions can occur. Imagine two stars, each already massive, slamming together in a cataclysmic merger. The resulting behemoth ignites with renewed fury, its surface temperature skyrocketing as it masquerades as a newborn star. Telescopes have spotted these imposters in clusters like Messier 30, where blue stragglers stand out like diamonds on black velvet, their brilliance a testament to the violence that birthed them. The implications ripple far beyond these clusters. Stellar cannibalism isn't just a curiosity, it's a galactic sculptor. When stars merge or strip material from one another, they alter the chemical makeup of their surroundings, spewing enriched gas back into space. This recycled material becomes the raw ingredients for future stars and planets, seeding the cosmos with heavier elements. Some theories even suggest that the most massive stars in the early universe might have grown to gargantuan sizes through relentless mergers, their explosive death seeding the cosmos with the first heavy elements. Yet the mystery isn't just about how often this happens, it's about the hidden players, binary systems, rogue planets, even black holes lurking in these clusters could act as gravitational puppeteers, nudging stars into fatal dances. Computer simulations reveal chaotic scenes where stars are flung outward like slingshots or dragged inward to their doom. In Omega Centauri, one of the Milky Way's largest globular clusters, Astronomers have detected stars moving at bizarre velocities, hints of past encounters that reshaped their trajectories forever. So what does this mean for galaxies? If stellar cannibalism is common, it could rewrite our understanding of how star clusters evolve. These violent interactions might explain why some clusters appear younger than they are, or why certain stars burn brighter long after their peers have faded. It's a reminder that in the cosmos, survival isn't just about endurance, it's about adaptation, theft, and sometimes sheer cosmic luck. And for blue stragglers, their stolen youth isn't a crime, it's a masterpiece of celestial rebellion. Some stars don't just drift through the galaxy, they sprint. Hypervelocity stars are the cosmic speed demons of the Milky Way, hurtling through space at millions of miles per hour, fast enough to escape the galaxy entirely. Unlike their stationary siblings, these rogue travelers didn't form in quiet nebulas. They were catapulted into the void by forces so violent they defy conventional stellar physics. Take SDSS J09's 0745, 0 plus 02 4507, one of the first hypervelocity stars ever discovered. This lonely blue giant is racing outward at over 900 kilometers per second, so fast it'll eventually leave the Milky Way behind entirely. But how? The leading theory points to Sagittarius A, the supermassive black hole at our galaxy's center. When a binary star system wanders too close, the black hole's gravity can tear the pair apart, capturing one star while flinging the other away at unimaginable speeds. It's like a cosmic slingshot, where the energy of the doomed star's orbit transforms into pure velocity for its ejected companion. Yet not all hypervelocity stars come from black hole encounters. Some might be survivors of supernovas in tight binary systems. When one star explodes, the sudden loss of mass can release its partner like a snapped rubber band, sending it careening across the galaxy. Others could be refugees from dwarf galaxies torn apart by the Milky Way's gravity, their stars scattered like billiard balls in a cosmic break. What's truly baffling is where these stars are headed. Many are on one-way trips into intergalactic space, destined to wander the eternal dark between galaxies. Others might eventually collide with distant gas clouds, triggering new rounds of star formation in their wake. And then there are the outlier stars moving too fast even for black hole ejections. Their existence hints at forces we don't yet understand, like dark matter interactions or primordial ripples in spacetime itself. These stellar fugitives aren't just curiosities, they're celestial breadcrumbs. By tracing their paths backward, astronomers can map the hidden gravitational landscape of the galaxy, pinpointing the locations of invisible black holes or dark matter clumps. Each hypervelocity star is a cosmic crime scene, its trajectory a clue to the violent event that launched it. So the next time you look up at the night sky, remember, not all stars are content to stay in place. Some are born to run, their journeys rewriting the rules of where and how a star's story can end. And as they vanish into the abyss, they carry with them secrets of the galaxy's most explosive encounters. The interstellar medium is the universe's ultimate recycling plant, a vast, invisible ocean of gas and dust drifting between the stars, so diffuse that in some regions there might be only a single atom per cubic centimeter. Yet despite its near-nothingness, this material holds the seeds of cosmic rebirth. Every star you see, every nebula that glows, was once just a wisp of this primordial haze, pulled together by gravity's patient hand. And right now, scattered across the galaxy, countless pockets of this interstellar fog are collapsing into the next generation of stars. Take the pillars of creation, those towering columns of gas in the Eagle Nebula, immortalized by the Hubble Space Telescope. What looks like a frozen sculpture is actually a chaotic construction site. Ultraviolet light from nearby stars bombards the pillars, eroding them like sandbanks in a cosmic tide. But inside that destruction, new stars are being born. The radiation that strips away gas also compresses it, triggering pockets of denser material to collapse under their own weight. It's a paradox. The same forces that tear down these structures also sculpt the conditions for starbirth. But how does something as tenuous as interstellar gas, so thin it's practically a vacuum, transform into a blazing star? The answer lies in shock waves, the cosmic domino effect that turns stillness into chaos. When a supernova explodes, its blast wave races outward at millions of kilometers per hour, plowing through nearby gas clouds like a bulldozer. The impact crumples the cloud's structure, creating dense knots where gravity can finally take hold. Similarly, the fierce winds from massive stars, hurricanes of charged particles streaming outward at supersonic speeds, can carve bubbles in the interstellar medium, their edges collapsing into stellar nurseries. The chemistry at work here is just as crucial as the physics. Interstellar clouds aren't uniform. They're laced with molecules like carbon monoxide and even complex organic compounds. These molecules act as cosmic refrigerators, radiating heat away and allowing the gas to cool. Without this cooling, the cloud would stay too hot to collapse. It's a delicate balance. Too much turbulence and the cloud shreds apart. Too little and it never condenses. But when conditions align, gravity amplifies tiny fluctuations, pulling material inward until the core ignites in a flash of nuclear fusion. What's astonishing is the scale of this recycling. The oxygen you breathe, the silicon in Earth's crust, the iron in your blood, all of it was forged in ancient stars and scattered into the interstellar medium by supernovas or stellar winds. Over billions of years, these atoms drift until they're swept up in a new cloud, destined to become part of another star, another planet, perhaps even another life form. The pillars of creation aren't just a sight to behold, they're a snapshot of a process that's been running since the dawn of time, a cycle of death and renewal written in gas and light. And the story doesn't end there. Some interstellar clouds are so massive they'll birth thousands of stars at once, their collective light and winds reshaping the surrounding medium for eons. Others, like the dark, dusty Bok globules, may condense in solitude, forming single stars wrapped in cocoons so thick they're invisible to optical telescopes. Yet all of them share one truth: the emptiness of space isn't empty at all. It's a reservoir of potential, a cosmic womb where the next act of creation is always just beginning. Every atom in your body, every breath you take, holds the echoes of stellar explosions older than Earth itself. When a massive star dies in a supernova, it doesn't just vanish, it scatters its guts across the cosmos, seeding space with carbon, oxygen, nitrogen, and iron. These elements, forged in the star's fiery core or synthesized in the explosion's unimaginable heat, become the raw materials for everything that follows: new stars, planets, and eventually life. It's the ultimate act of cosmic generosity, a stellar death gifting the universe with the building blocks of creation. Take something as simple as the calcium in your bones. Most of it wasn't made during the Big Bang or in the quiet fusion of small stars. It was likely born in the last frantic moments of a supernova, when shockwaves ripped through the dying star's layers, triggering runaway nuclear reactions that cooked lighter elements into heavier ones. The same goes for the iron in your blood, a relic of stellar furnaces so hot they could fuse atoms into metal. Even the gold in your jewelry, that probably came from two neutron stars colliding, a cataclysm so violent it spewed precious metals across the galaxy like cosmic confetti. But how do these elements travel from a supernova's wreckage to a planet or a person? The answer lies in the gentle but relentless push of stellar winds and the explosive force of the supernova itself. When a massive star nears death, its outer layers become unstable, shedding gas laced with newly minted elements into space. Then, when the core collapses and the star detonates, the blast hurls the remaining heavy elements outward at nearly a tenth the speed of light. Over millennia, these fragments mix with interstellar gas, becoming part of vast molecular clouds, the same clouds that collapse to form new stars and planets. This recycling isn't just poetic, it's measurable. Astronomers can trace the chemical fingerprints of these elements in stars of different ages. Younger stars, like our Sun, are richer in heavy elements than their ancient predecessors, proof that each stellar generation builds on the ashes of the last. Even more astonishing, we've caught this process in action. In the remnants of supernovas like Cassiopeia A, telescopes have spotted swirling clouds of oxygen, sulfur, and silicon elements that will one day be incorporated into future worlds. The implications are humbling. The nitrogen in your DNA, the oxygen filling your lungs, even the sodium that lets your nerves transmit signals, all of it was once part of a star that died before our solar system existed. You aren't just observing the cosmos, you are the cosmos, a living collection of atoms that have journeyed across space and time to form you. This isn't metaphor, it's astrophysics. Yet the story doesn't end there. Some theories suggest this recycling isn't uniform. Galaxies might have chemical gradients, where elements are distributed unevenly based on their distance from the galactic center. Stars born in crowded regions could inherit more heavy elements than those in the outskirts, affecting the kinds of planets and potentially life that form around them. Other models propose that certain elements, like gold and platinum, might be so rare because they're only produced in the most extreme cosmic events, like neutron star mergers. So when you look up at the night sky, remember, you're not just seeing stars, you're witnessing a chain of creation that stretches back billions of years, where every ending is a beginning in disguise. The universe doesn't waste a single atom. It transforms, recycles, and rebuilds, turning stardust into worlds, and worlds into stories like yours. The universe is a paradox. It builds life with one hand while wiping it out with the other. Supernovas, those dazzling stellar explosions that seed galaxies with life-giving elements, might also be the universe's ultimate sterilizers. Picture a star exploding just a few dozen light-years away. Its gamma ray burst slicing through space like a scythe, stripping atmospheres and irradiating entire planets. This isn't science fiction, it's a real cosmic gamble, one that could answer one of astronomy's most haunting questions. If the universe is so vast, why does it feel so empty? The idea, known as the Great Filter, suggests that some universal hurdle prevents life from flourishing, and supernovas might be that barrier. When a massive star collapses, it doesn't just explode. It can unleash a focused beam of gamma rays, the most energetic form of light, capable of frying DNA and vaporizing ozone layers from hundreds of light years away. Evidence suggests Earth may have endured such an event 2.5 million years ago, when a nearby supernova potentially triggered a mass extinction by bombarding our planet with radioactive iron isotopes, traces of which are still buried in ancient seafloor sediments. Yet without these same cataclysms, life as we know it wouldn't exist. The oxygen we breathe, the iron in our blood, even the uranium that heats Earth's core, all were forged in supernovas. It's a brutal trade-off. The same explosions that might snuff out life also provide its essential ingredients. This duality raises a chilling possibility. What if the reason we haven't found other civilizations isn't because they're rare, but because they've been erased? Galactic habitable zones, regions far enough from stellar death traps yet rich in heavy elements, might be narrower than we think. But here's the twist: life might be more resilient than we assume. Some extremophiles on Earth thrive in radiation levels that would kill humans, hinting that microbial life could survive even a nearby supernova. And not all stellar explosions are equal. Only the rarest, most perfectly aligned gamma-ray bursts pose a galaxy-wide threat, while most supernovas sterilize only their immediate cosmic neighborhood. The odds of a planet being both close enough to a supernova for annihilation and far enough from earlier ones to have the right elements might be vanishingly small, or perfectly balanced for life to emerge in fleeting, golden windows. The debate isn't just academic, it shapes how we search for extraterrestrial life. If supernovas are the great filter, we should focus on galaxies with low star formation rates, where explosions are less frequent. Alternatively, if life can endure, we might expect to find it clustered in the safe zones between spiral arms, where stellar density and supernova risk is lower. Either way, the silence of the cosmos might not be a sign of absence, but a scar left by the very forces that made our existence possible. So while supernovas giveth and taketh away, their paradox reminds us the universe isn't just a stage for life. It's a minefield, one we've somehow miraculously navigated. Some stars defy every rule we thought we knew, cosmic anomalies so extreme they rewrite the textbooks. Take magnetars, for instance. These neutron stars don't just have strong magnetic fields. Their fields are so intense they could strip the data from every credit card on Earth from halfway across the galaxy. A magnetar's magnetic grip is a quadrillion times stronger than our planet's, twisting its crust until it fractures in violent starquakes, unleashing bursts of gamma rays brighter than 100,000 suns. In 2004, one such flare from 50,000 light-years away actually disrupted Earth's ionosphere, proof that these objects aren't just curiosities. They're celestial monsters lurking in the dark. Then there are Thorn-Zitkow objects, stellar hybrids so bizarre they sound like science fiction. Picture a red supergiant, swollen to hundreds of times the sun's size, but hiding a neutron star at its core like a cosmic Russian doll. This isn't just a star with a dense heart, it's a gravitational paradox. The neutron star, born from a supernova, somehow avoided being flung away and instead spiraled into the core of its giant companion. Now the two exist in a precarious dance, with the neutron star slowly devouring the supergiant from within. These objects are so rare and short-lived that astronomers debate whether any still exist, but if they do, their peculiar fusion processes could produce elements unlike anything seen in ordinary stars. But what if stars aren't made of just neutrons or protons? Enter strange stars, hypothetical objects where the crushing gravity transforms ordinary matter into strange quark matter, a primordial soup of quarks freed from their usual confines. In this state, up and down quarks, the building blocks of protons and neutrons, mingle with strange quarks, a heavier, more exotic variety. The result: a star so dense it could pack the mass of the Sun into a sphere the size of Manhattan, yet with a surface harder than diamond. If these stars exist, they'd be nearly indestructible, their cores possibly older than the galaxy itself. The most mind-bending part: these exotic stars aren't just cosmic oddities, they're laboratories for physics we can't recreate on Earth. Magnetars push the limits of electromagnetism. Thorn-Zitkow objects challenge our models of stellar evolution, and strange stars could redefine our understanding of matter itself. Each one forces us to ask, what else is out there, lurking in the dark, waiting to shatter our assumptions? The universe, it seems, has a flair for the dramatic crafting stars that don't just shine, but defy reality itself. The Pleiades sparkle like a handful of diamonds tossed across the night sky, a tight-knit family of young, hot stars born from the same cosmic womb. But this celestial siblinghood won't last forever. Open star clusters, those glittering assemblies of stellar siblings, are born together in swirling nebulas, bound by gravity's embrace. Yet over millions or billions of years, they slowly unravel, their stars scattering across the galaxy like dandelion seeds in a cosmic wind. This isn't just a quiet farewell, it's a transformation that reshapes the very fabric of the Milky Way. So what tears these families apart? The answer lies in a tug of war between gravity and chaos. When a cluster first forms, its stars are swaddled in the remnants of their birth cloud, a cushion of gas that helps stabilize their orbits. But as radiation from the hottest members blows this gas away, the cluster loses its anchor. Without this buffer, even the gentle gravitational nudges from passing gas clouds or the Milky Way's tidal forces stretching pulls from the galaxy's overall gravity and destabilize the system. Stars begin to drift, their velocities altered by chance encounters with one another, until the cluster's grip weakens entirely. The speed of this dissolution isn't random. Dense clusters like the beehive in Cancer can hold themselves together for hundreds of millions of years, their stars packed so tightly that gravity dominates. But looser groups like the Alpha Persei cluster may disperse in just a few tens of millions of years. Even the Pleiades, now 80 million years old, shows signs of fraying at the edges, its faintest members already slipping away into the galactic background. Where do these orphan stars go? Some join the Milky Way's vast field star population, solitary wanderers orbiting the galaxy's center alone. Others might be captured by passing star clusters or drawn into the gravitational embrace of giant molecular clouds, becoming part of new stellar nurseries. Remarkably, astronomers can sometimes trace these escapees back to their birth clusters by matching their chemical fingerprints unique ratios of elements that act like cosmic DNA, betraying their shared origins. But the real surprise is how these drifting stars shape galactic evolution. As clusters dissolve, they seed the galaxy's spiral arms with fresh stars, contributing to the Milky Way's intricate structure. Some theories even suggest that our Sun might have been born in a long-vanished cluster, its siblings now scattered beyond recognition. If true, every star we see, even our own, could be part of a diaspora stretching back billions of years, a testament to the impermanence of cosmic families. Yet some clusters defy the odds. A rare few, like Messier 67 in Cancer, have survived for nearly 5 billion years, nearly the age of the galaxy itself. These ancient survivors likely owe their longevity to their location in the Milky Way's quieter outskirts, far from the disruptive gravitational tides of the crowded inner galaxy. They're the cosmic equivalents of hermits, enduring by avoiding the chaos that shattered their peers. So the next time you spot the Pleiades, remember, you're not just seeing a pretty star cluster. You're witnessing a fleeting moment in a cosmic life cycle, a snapshot of a family destined to drift apart. Their eventual separation isn't tragedy, it's transformation. Each scattered star carries the legacy of its birthplace into the galaxy's vast tapestry, ensuring that even in dispersal, there's no true end. Globular clusters are the universe's ancient metropolises, dense, glittering cities of stars that have thrived for nearly as long as the cosmos itself. Imagine a sphere crammed with hundreds of thousands, sometimes millions, of stars packed so tightly that a single light year could contain thousands of them. Our Milky Way hosts about 150 of these relics, each a fossilized snapshot of the galaxy's fiery youth. Unlike the fleeting open clusters, which dissolve over mere millions of years, globular clusters endure for billions, their stars bound together by gravity's unrelenting grip. What makes these clusters so extraordinary isn't just their age, it's what they've witnessed. The stars in globular clusters formed when the universe was still in its infancy, composed almost entirely of hydrogen and helium. They lack the heavier elements that pepper younger stars like our Sun, making them cosmic time capsules preserving the chemical makeup of the early cosmos. In their light, astronomers read clues about how galaxies assembled, how stars age, and even how the first seeds of structure emerged after the Big Bang. But the real mystery lies at their hearts. Many globular clusters exhibit bizarre stellar motion stars orbiting something invisible at breakneck speeds. The leading explanation, intermediate mass black holes lurking in the cores like silent predators. These black holes, weighing thousands of solar masses, could be the remnants of the cluster's violent past, where countless stars collided and merged over eons. Others speculate the gravitational anomalies might stem from dark matter, though globular clusters were long thought to lack it. If true, it would upend our understanding of how these structures formed. Then there's the paradox of their survival. In such crowded environments, stars should collide frequently, tearing each other apart or merging into bizarre hybrids. Yet globular clusters persist, their stars aging gracefully despite the chaos. Some theories suggest they've undergone a process called core collapse, where gravitational interactions slingshot stars outward, leaving a dense central core that stabilizes the system. Others propose that black holes act as cosmic bouncers, ejecting disruptive stars and maintaining order. The most fascinating outliers are the blue stragglers, stars that appear inexplicably young amid their ancient neighbors. These celestial anomalies defy time, either by stealing mass from companions or merging outright, rejuvenating themselves in a cosmic fountain of youth. Their presence hints at the dynamic, almost Darwinian struggle for survival within these clusters, where stars don't just coexist, they compete. Globular clusters aren't just relics, they're living laboratories. Their tightly packed stars offer a preview of what happens in galactic cores, where black holes and stellar densities reach extremes. Some may even be the stripped nuclei of dwarf galaxies, devoured by the Milky Way long ago. As telescopes peer deeper into their secrets, one thing becomes clear. These ancient stellar cities aren't just survivors. They're storytellers, their light carrying whispers from a time when the universe was young and everything was possible. Quasars blaze across the cosmos like cosmic lighthouses, their brilliance outshining entire galaxies from billions of light years away. At their cores, supermassive black holes, some weighing billions of suns, devour swirling disks of gas with such ferocity that the friction heats the material to millions of degrees, unleashing torrents of radiation across the electromagnetic spectrum. These are the most energetic engines in the universe, capable of shaping not just their host galaxies but entire galactic neighborhoods. Yet their influence on star formation is a paradox of destruction and creation, a celestial push and pull that can either stifle stellar birth or ignite it with startling violence. Picture a galaxy falling under a quasar's spell. As the black hole feasts, it spews jets of charged particles and radiation at near light speeds, carving through surrounding gas clouds like a cosmic blowtorch. This relentless barrage heats the galaxy's interstellar medium, preventing it from cooling and collapsing into new stars. Astronomers call this quasar feedback, a process so potent it can leave massive galaxies filled with aging stars but devoid of newborn stellar graveyards frozen in time. The nearby galaxy Messier 87 offers a glimpse of this phenomenon. Its supermassive black hole driving winds so powerful they've blown away star-forming gas for thousands of light years. But quasars aren't just agents of suppression. In some cases, their fury can compress gas clouds along the edges of their jets or shockwaves, triggering intense bursts of star formation. It's like a cosmic domino effect. The quasar's energy slams into a molecular cloud, squeezing it until gravity takes over, collapsing the cloud into clusters of massive, short-lived stars. The Spiderweb Galaxy, a chaotic system 7 billion light-years away, showcases this duality. Here, a quasar's radiation suppresses star formation in its immediate vicinity. Yet at its outskirts, newborn stars ignite in frenzied waves, their birth fueled by the same forces that stifle it elsewhere. The key lies in balance. Quasars operating in gas-rich environments can create conditions where star formation cascades in ripples, like throwing a stone into a pond. The initial shockwave might heat the inner regions, but the recoiling pressure can slam into cooler gas farther out, sparking stellar nurseries where least expected. Some theories even suggest that quasars played a crucial role in the early universe, their outbursts distributing heavy elements forged in supernovas across vast distances, enriching future generations of stars and planets. Yet the most intriguing question remains: do quasars dictate a galaxy's fate, or do they respond to it? Observations reveal that the most luminous quasars often inhabit galaxies already teeming with star formation, suggesting a symbiotic relationship. The same gas that feeds the black hole also fuels stellar birth, creating a feedback loop where the quasar and the galaxy evolve together. Over cosmic time, the quasar's outbursts may grow quieter as it exhausts its fuel, allowing the galaxy to settle into a quieter, more stable phase, a cosmic adolescence giving way to maturity. So while quasars might seem like destructive monsters, they're also cosmic sculptors, their influence weaving through the life cycles of stars and nebulas in ways we're only beginning to understand. Their light, traveling across billions of years, carries not just the story of their own power, but the blueprint of how galaxies, and perhaps life itself, came to be. The cosmos has a way of hiding its ghosts. When massive stars die, they should leave behind white dwarfs, neutron stars, or black holes, stellar tombstones marking their final resting places. But astronomers face a haunting discrepancy. The numbers don't add up. Based on the Milky Way's star formation history, there should be millions more stellar remnants lurking in our galaxy than we've actually detected. So where are they all hiding? One possibility is cosmic camouflage. Imagine a white dwarf cooling over billions of years until it emits only a faint infrared glow. Now shrouded in a thick cloak of interstellar dust, perhaps debris from its own planetary system, torn apart during its red giant phase. Such an object would vanish from optical surveys, detectable only by the subtlest heat signatures or gravitational microlensing events. The same goes for neutron stars that have drifted into dense molecular clouds, their faint X-ray pulses smothered by gas and dust. These remnants aren't truly missing, they're just masters of disguise, blending into the galaxy's shadowy backstreets. Then there's the Great Galactic Escape. Some stellar corpses might have been flung out of the Milky Way entirely, victims of gravitational slingshots during close encounters with other stars or black holes. Hypervelocity neutron stars rocketing through intergalactic space at thousands of kilometers per second could already be beyond our detection limits, their radio pulses too faint to hear over the cosmic noise. Even more intriguing are white dwarfs ejected during the chaotic breakup of binary systems. When one star in a pair goes supernova, the explosion can kick its companion, now a lone white dwarf, out of the galaxy's grasp like a stone from a sling. But the most radical theory suggests these remnants never existed in the first place, at least not in the forms we expect. If certain stars collapse directly into black holes without the fanfare of a supernova, they'd leave no neutron star behind, just an invisible gravitational pit. Observations of failed supernova, where massive stars vanish without the expected explosion, lend credence to this idea. Alternatively, some remnants might have morphed into exotic objects we don't yet recognize, like quark stars or even dark matter entities that defy current classification. Solving this cosmic census crisis isn't just academic. The missing remnants hold clues to the galaxy's chemical evolution, the frequency of black hole formation, and even the distribution of dark matter. Future telescopes like the Vera Rubin Observatory or the Square Kilometre Array could uncover these ghosts by scanning for subtle gravitational distortions or faint radio whispers. Until then, the galaxy's hidden dead remind us that even in the vastness of space, some secrets refuse to be found, only patiently, relentlessly pursued. The sun may seem eternal in our skies, but its destiny is written in the same cosmic laws that govern every star. 5 billion years from now, the hydrogen fuel in its core will finally dwindle, triggering a transformation that will reshape the solar system forever. As fusion slows, the sun's core will contract, heating up until its outer layers swell into a red giant, a bloated, crimson behemoth large enough to swallow Mercury, Venus, and likely Earth itself. The oceans will boil away, the mountains melt into magma, and our planet's atmosphere stripped by the sun's furious stellar winds. It's a fate that sounds apocalyptic, but in the grand timeline of stars, it's just another chapter in an inevitable cycle. Yet this expansion isn't just about destruction. As the sun grows, its increased luminosity will temporarily warm the outer solar system, turning frozen moons like Europa and Enceladus into temporary havens. Their icy shells could thaw, creating subsurface oceans where life might briefly flourish. Even distant Pluto, now a frigid world at the solar system's edge, could experience a fleeting spring as the dying sun's warmth reaches it for the first time. This paradoxical dance where inner worlds are consumed while outer ones awaken shows how stellar death is as much about transformation as annihilation. The sun's final act will be quieter but no less profound. After shedding its outer layers in a shimmering planetary nebula, its exposed core will collapse into a white dwarf, a dense, Earth-sized ember that will glow faintly for trillions of years. This remnant will be rich in carbon and oxygen, the ashes of the sun's nuclear fires, and it will slowly cool into a black dwarf, a cold, dark relic. But the nebula around it will tell a different story. Glowing with the light of ionized gases, it will disperse into the galaxy, carrying elements that might one day seed new stars, planets, or even life. Could future civilizations witness this transformation? If humanity or its descendants still exist, they'd need to have migrated far beyond Earth to survive. Some theories suggest advanced societies might harness the energy of the red giant sun, or even engineer ways to prolong its life by siphoning material from other stars. Others imagine spacefaring cultures watching from distant colonies, recording the sun's death as both a scientific event and a cultural milestone. But even if no one is left to see it, the sun's legacy will endure. Its expelled material will mix with interstellar clouds, contributing to the next generation of stars, and its white dwarf core will drift through the galaxy as a silent monument to the system it once ruled. What's most humbling is the scale. The sun's death will unfold over billions of years, a slow-motion finale that no single civilization could witness in full. Yet in that gradual fade, there's a strange kind of poetry. The same star that gave Earth light and life will one day reclaim it, scattering its atoms back into the cosmos. And in doing so, it will ensure that the story doesn't end. It simply changes form, like stardust on an infinite wind. The universe is a story with no clear ending, yet every star, every nebula, is a clue to how that story might close. Right now, galaxies are racing apart, carried by the momentum of dark energy, an invisible force stretching space itself. If this expansion continues unchecked, the cosmos could face a slow, quiet demise known as heat death. Picture a future so distant that all stars have burned out, black holes have evaporated, and the universe is reduced to a thin, cold haze of particles drifting endlessly in the dark. No light, no heat, just entropy's final whisper. In this scenario, the life cycles of stars aren't just a spectacle, they're a countdown to stillness. But there's another possibility, one far more dramatic. What if dark energy weakens or gravity gains the upper hand? Instead of endless expansion, the universe could reverse course, collapsing inward in a cataclysm called the Big Crunch. Galaxies would rush toward one another, space itself contracting until everything, stars, planets, even space-time, is compressed into a singularity. It would be the ultimate cosmic recycling, a fiery rebirth where the density and heat mirror the conditions of the Big Bang itself. In this version of the end, stellar remnants like white dwarfs and neutron stars wouldn't just fade, they'd be obliterated, their atoms fused into something entirely new. The key to these opposing fates lies in the very stars we've been studying. The way they live and die shapes the universe's trajectory. Every supernova enriches the cosmos with heavy elements, while every dying star's expelled gas feeds future generations. But there's a catch. The more the universe expands, the harder it becomes for that material to coalesce into new stars. Over trillions of years, star formation will sputter out, leaving only the longest-lived red dwarfs glowing faintly in the void. If heat death is the future, these embers will be the last witnesses to the era of light. Yet some theories suggest a middle path. Could dark energy's influence change over time? If it weakens, the universe might avoid both heat death and a big crunch, settling into a state of equilibrium where expansion slows but never reverses. In this scenario, stellar remnants would endure, their slow decay marking time in a universe neither dying nor reborn, but simply persisting. It's a humbling thought. The fate of everything might hinge on forces we've only begun to detect, let alone understand. What's certain is that the life cycles of stars are more than just local events, they're threads woven into the universe's ultimate destiny. Whether it ends in fire, ice, or something beyond our imagination, their stories are the prologue to the final chapter. And as we piece together those stories, we're not just studying the past or present, we're reading the first lines of the cosmos' last poem. For every cosmic mystery we've unraveled, there are dozens that still defy explanation, enigmas so perplexing they challenge the very foundations of astrophysics. Take Tabby's star, officially known as KIC 8462852, a seemingly ordinary sun-like star that dims unpredictably by up to 22% for days or weeks at a time. No known natural phenomenon, not planets, not dust clouds, fully accounts for these erratic dips. Some have even speculated about alien megastructures, though most astronomers favor more mundane, if equally puzzling, explanations like swarms of comets or exotic dust formations. The truth, we still don't know, and that's what makes it thrilling. Then there are fast radio bursts, those millisecond-long blasts of energy so powerful they outshine entire galaxies for the briefest moments. First detected in 2007, these cosmic flashes seem to come from deep space, some repeating in patterns that defy easy categorization. While some bursts have been traced to magnetars, highly magnetic neutron stars, others originate from regions with no obvious stellar remnants, leaving researchers scrambling for answers. Are they the screams of colliding black holes, the death throes of evaporating primordial objects, or something entirely new, a phenomenon we haven't even imagined yet? Each new detection deepens the mystery, but the puzzles don't stop there. Consider the Great Attractor, a gravitational anomaly pulling entire galaxies, including our own Milky Way, toward it at over 600 kilometers per second. Hidden behind the dust of the Milky Way's central plain, this invisible behemoth challenges our maps of cosmic structure. Is it a massive cluster of galaxies we can't see? A flaw in our understanding of dark matter's distribution, or evidence of something even stranger lurking in the cosmic shadows? Even nebulas, those seemingly well-understood stellar nurseries, harbor secrets. Why do some, like the Boomerang Nebula, register as the coldest natural place in the universe at just 1 degree above absolute zero? How do others, like the Red Square Nebula, form near-perfect geometric shapes, structures so precise they look almost artificial? And what about the runaway stars like Zeta Ophiuchi, plowing through interstellar gas at breakneck speeds, leaving shockwaves in their wake? Were they ejected by supernovas or gravitational tugs from unseen companions? The most humbling part, every answer seems to birth new questions. Dark matter's role in star formation, the true nature of rogue planets between stars, the origins of ultra-high-energy cosmic rays, all remain wide-open frontiers. These aren't just gaps in knowledge, they're doorways to discoveries that could rewrite textbooks. And that's the beauty of astronomy. The universe isn't just a puzzle to be solved. It's an endless conversation, one where each revelation pulls back another layer of the unknown, reminding us that the cosmos still has secrets it's not ready to give up. From the swirling stellar nurseries where stars are born to the explosive supernovas that scatter their ashes across the cosmos, we've traveled through 25 of the most extraordinary theories shaping our understanding of stellar life cycles. But here's the breathtaking truth. Every answer we've uncovered only peels back another layer of mystery. Take the humble protostar. What seems like a straightforward collapse of gas and dust hides quantum complexities we're still unraveling, from magnetic fields that braid like cosmic DNA to jets that defy classical physics. Or consider the enigma of dark matter's shadowy influence on star formation, a puzzle where each new observation seems to rewrite the rules. The beauty of astronomy lies in its endless frontier. Just decades ago, black holes were theoretical curiosities. Now we've captured their shadows and detected their collisions. Who's to say what revelations await? Perhaps we'll find stars powered by dark matter, or neutron stars hiding portals to exotic physics. Maybe the key to quantum gravity lurks in the vibrations of a magnetar's crust, or a distant nebula holds clues to life's cosmic origins. The universe doesn't just hold secrets, it thrives on them, daring us to look deeper. And that's why this journey doesn't end here. Every night, telescopes from mountaintops to space orbiters scan the skies, gathering data that could upend our theories tomorrow. Citizen scientists comb through star charts, uncovering anomalies that professional astronomers might miss. Even your gaze upward, whether through a backyard telescope or just your naked eyes, connects you to this grand exploration. Because the cosmos isn't some distant spectacle, it's a living, evolving story, and we're all part of it, so stay curious. The next time you see Orion's belt or the smudge of the Andromeda galaxy, remember, you're witnessing chapters in a saga billions of years in the making, with twists still being written. And if these theories have sparked your imagination, hit like, subscribe, and join the conversation below. What cosmic mystery fascinates you most? The universe is listening, and who knows? The next great discovery might just begin with a question from someone like you. Keep looking up. The stars have so much left to tell us.